a window they have open rather than Chrome?
Yes, window.
Oh, window.
Okay, let's put it full screen and we are set. Okay, welcome everybody. Sorry for the delay and technical problems. So it's a pleasure to welcome Brenda and Guilfoyle from Worcester University, and we talk about the title of the talk will be from CT scans to 4-Manifold Topology. Thank you.
Thank you, and thank you for the invitation to talk. Actually, it's not often that I get the chance to, it's the first time I've spoken initially in a long time, but actually the basis of what I'm doing, you could probably go back 500 years, 600 years. If you look at some of Leonardo's manuscripts, he talks about the air is full of an infinity of straight lines and rays, which cut across each other without displacing each other. So he's kind of saying you're looking at a set of lines or oriented lines being rays, and you view them as individual objects. He's kind of defining the space of oriented and unoriented lines in R3 in this case. Now he says which reproduce on whatever they encounter the true form of their cause, which seems to suggest there's information being traveled from the source to the observer and nothing is lost in between. That may be a little bit of a stretch. In particular, what I'm going to be talking about is in fact what's called the X-ray transform. And here it does a little bit more. What the medium through which your light is traveling, in fact, reduces the intensity of the light. So it actually does kind of what it passes through does lose a little bit of information in some sense. And this is the thing that I'm going to talk about today. Now I'm going to be doing it in R3, but in general, the idea is what's called the X-ray transform. And the idea is that if you're given a function from R to R, real valued function, you can define a new function by the space of all oriented lines. I'll take the oriented lines arrays as Leonardo called it. Really, it's the space. You can just add an orientation. Of course, it's just a choice of one of two directions. And it defines a function then. This L of Rn is the space of oriented affine lines, not through the origin, not like in algebraic geometry, where of course you look at complex lines through the origin. And here we're looking at the space of all oriented affine lines in Rn. And the idea is that, I guess, if you have a light ray passing through some density, it'll end up with a loss in the intensity of the light. And this, I guess, geometric optics is one of the names that is adopted for this. And in the case of, well, in Rn, the space of oriented lines in Rn is in fact the tangent space to Sn-1. So it's a 2n minus 2-dimensional manifold if you look at the space of all oriented lines. And for low dimensions, well, the dimension of R2, the space of oriented lines, is 2-dimensional. But in R3, it jumps to 4. So if you look at the kind of inverse problem where you're given a function on the space of lines, you could ask, does it come from a function in R3? Or Rn in particular. So again, this is the inverse problem, and it has many, many applications. And the answer is, well, it depends on the dimension. So for n equal to 2, the space of oriented lines is also 2-dimensional. So you can expect that you can reconstruct the function directly from its integral over all lines in the plane. So this is what's called the radon transform, and the inverse radon transform, then the reconstructing the function from its integrals over all lines in the plane. Now the case we're going to be looking at though is just it's R3. And so your function in R3 is a function of 3 variables, but your space of oriented lines is now 4-dimensional. So there's a redundancy. So this redundancy in looking at something from trying to reconstruct something from its integral over lines is going to have a little bit more information than you want. In fact, there's 2 different ways that you could proceed if you want to. You know that it's integral over lines and you want to reconstruct the function. This is what we call the inverse problem. You could find some kind of compatibility conditions maybe on U. If you know it over the whole 4-dimensional space, you might then look to see what restrictions there are on such a function for it to come from an integral over lines in R3. The other thing you could do is just cut down the dimension, and instead of saying this function u is defined in all four-dimensional space-oriented lines, is just to take it over three-dimensional space, submanifold. So these are two different kind of ways that you could look at it. Look at it as a function on four-dimensional space with some equation, and on the other some restriction on it, a compatibility condition, or you could just prescribe it on a three-dimensional submanifold and then extrapolate it out. Now, in 1938, in a seminal paper by Fritz John, so here I'm talking about compactly supported functions, but in fact you could do this if they have the right asymptotic fall off at infinity. So if you're given a function on the space of lines, we want to know when does it come from an integral of a function in R3. And the answer is that it satisfies, this is true again, compactly supported. You could also extend this to ones that have the right fall off at infinity. In any event, what you find is that you get a rather unusual equation. It's called the ultra-hyperbolic equation. Now, the ultra-hyperbolic equation, so that's a second order homogeneous operator, but the eigenvalues are plus of the symbol are plus, plus, minus, minus. Okay, so this is an extremely unusual signature for a metric in the sense that, of course, from relativity, you look at ones which are plus, plus, plus with a single minus. Of course, so life is always easier in the definite case as well. So Riemannian manifolds, you would take plus, 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 plus. But here, what you find is that, in fact, you have this what's called ultra-hyperbolic equation. Right? So it's called an ultra-hyperbolic equation, and you could define it in n dimensions in this various, but I'm going to specifically talk about this four-dimensional case. Okay, so one of the problems with dealing with that equation is that,
a question. Is there an intuitive reason for which the first two coordinates have the plus and the
not really. It's
minus?
rather hard to see that, to be honest. I will show you. You can, I'll relate it to the geometry. So one of the things I guess you could say here, this is just a PDF written down in terms of coordinates. You have some nice coordinates wherever they came from. But what is the geometry behind this, right? So what we have to have is some kind of geometry in the space of oriented lines. And then what we would like is that this is the Laplacian. Okay, and in that setting, then you could maybe say, well, what is this plus plus and what is this minus minus? And well, essentially, we'll see. Well, I may not quite explain it fully, but the idea is that if you take an oriented line and you move it, there's lots of different ways that you can move it. But if you move it so that it's parallel, that's like a two-dimensional direction. That's like one of these.
Okay, this is I expected something like that.
And if you rotate it, then you get what.
But y rotations are the minus
exactly.
and y the translations the plus.
Exactly. Translations and rotations are very intimately connected with this equation. Now, in 1938, there was no attempt to geometrize this equation. Essentially, what I'm going to do now is I'm going to explain the geometrization of this equation invariant, which is related to the Laplacian of a canonical metric. Okay, but this canonical metric has got to have signature 2, 2. Okay, and that's suddenly something that's well outside of the normal thing. Of course, we're used to Lorentz manifolds where it might be 3 pluses and 1 minus, which of course comes up in relativity. And you could or it could be plus, 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 you know. Originally, when I discovered this, I was, originally I found this myself and only went back to Fritz John and discovered in the 30s that this was known back then. I did everything to try and change those two signs because we like things to be positive definite. When the positive definite and the norm is 0, the function is 0, etc. So, it's more the comfort zone of positive definiteness. If you're in relativity, of course, plus, 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 minus, that's not a problem either. The special things happen in that case. But here we have something that falls in between what's called the ultra-hyperbolic equation. Generally, it's been avoided, even though it obviously comes up in a very natural way. And I'll show you at least one way in which it turns up quite naturally. But one of the things that unfortunately worked against it was that Courant and Hilbert, in their first edition of their classical mathematical physics, showed that the ultra-hyperbolic equation does not have a well-posed boundary value problem for data defined on an arbitrary three-dimensional submanifold of the space of lines. So this makes it suddenly, we're not so interested in. And this was prior to Fritz John, I would say. And Fritz John came and did this, and what he showed is that there are characteristic hypersurfaces where it is, in fact, a well-posed boundary value problem. So it kind of got a bad reputation from Courant and Gilbert initially because they said, oh, here's an example of something that doesn't have a good initial value problem, which physically is something that you would like for most physical theories. But on the other hand, Fitzjohn came back and said the following. You can solve the autohyperbolic equation if you give characteristic boundary value problems, boundary values. So not an arbitrary three-manifold are you able to reconstruct this function if you're given that data on the three-manifold, but for ones that are characteristic. Now, I'll explain exactly what characteristic is in a minute, but for example, the one that Fitzjohn did in example in detail in his paper, he took the three-dimensional set of lines that are parallel to a fixed plane. Okay, so in that case, every line, say, is pointing either in some circle or in some parallel to some plane. That's a three-dimensional set, and in fact, possibly, if you could say, the closest that mathematics has ever come to winning a Nobel Prize was in fact this in 1973, where McCormack, he did the theoretical side of it, showed that in fact you could invert this data that you get from integration over lines if by using such a three-dimensional hypersurface. So from three-dimensional data on a three-manifold, you can actually get all the information inside. Now this three-dimensional set of lines parallel to a plane, it's kind of geometric, but at the same time, it's not exactly, we don't really have a metric in here yet. We haven't really mentioned what metric to use. So in fact, this is probably going to be claimed that this is the closest that pure mathematics has ever gone to getting a Nobel Prize, was in fact this theoretical thing. Now, Radon had done something similar in the 30s, or maybe in the 20s. But essentially the idea is you look at all the oriented lines in the plane, and then you can invert it on that plane. If you do that over all these parallel planes, then you can reconstruct the function from essentially the two-dimensional inversion form of the radon transform. Okay? Because the oriented lines in 2 dimensions is two-dimensional. So you can expect to reconstruct on a plane, which you can't when you have more information in 3 dimensions, and this is a way of cutting it down. And then you can reconstruct it, and then you have it on the whole 4-manifold. Okay, so again, Fitzjohn came out in 38 and gave this very, very beautiful description of it. And in later versions of Courant and Hilbert, they do mention John's theorem, and they explain that this is obviously quite interesting in that you can't prescribe it on an arbitrary 3-manifold, but this you seem to be able to describe it. This is a characteristic 3-manifold, or a null one as we would call it, and somehow it works in that case. Now, my own involvement with this was to look at just the space of oriented lines and to see if we could find an invariant metric. Originally, I hadn't even known Fitzjohn's work at this point, looking for a neutral metric, well, in fact, looking for any metric on the space, the 4-dimensional space for oriented lines, which is invariant under the Euclidean group. So what you'd like is that the space of oriented lines of your space somehow capture the geometry of the underlying space. Okay, and it turns out that for a 4-manifold, in fact, this only works in 4 dimensions. If you work in R2 or R4 or any higher dimension, there's more compatibility conditions, get much more complicated, and there is no canonical neutral structure on this manifold. So what do I mean by neutral? So it's a metric of signature 2,2. You saw the flat version of it just there, ddx squared plus dx1 squared plus dx2 squared minus the other 2 variables squared. So this here tells you that in fact this metric G gives you that. It is in fact the Laplacian of this metric in some sense that you're looking at. So it's a geometrization of Fitzjohn is what is included in this. Now, the issue here is that, well, it's lovely, it has lots of nice structure. It has a metric, it has a canonical complex structure, which was used by Hitchin in a study on monopoles, actually, the complex structure on its own, but it also has this symplectic structure. So closed non-degenerate 2 form. So it's a Kähler, what we would call Kähler in geometric terms, but it's neutral Kähler in that the metric has this signature 2,2. Now everything else about it is beautiful. They're compatible. You go from the metric to the symplectic structure using the complex structure. So somehow it's a natural structure, except for this bizarre signature 2-2, which somehow makes it a little bit outside of relativity and also outside of modern mathematics, where we like to work with Riemannian objects, you know, where square norms being 0 means the underlying function is 0. So one of the things that's also strange about this structure, that it only exists in Rn for n equal to 3. So it doesn't work in any other dimension, lower or higher. There is no such canonical invariant metric. And when I say invariant under the action of the Euclidean group. And so it's the natural metric if you're going to be using this 4-dimensional space to model what's going on in R3. Okay, so given that, the metric is conformally flat. As I said, it's also scalar flat, and Fluker had found these coordinates for line space, and in fact, it shows that the metric is conformally flat, and these coordinates, these Fluker coordinates, are in fact exactly the conformally flat coordinates for this this metric. Now, so funnily enough, then what we can say is that this ultra-hyperbolic operator, this flat ultra-hyperbolic operator, comes about because it's conformally flat, and you can in fact just pull this conformal factor in here, and you have the Laplacian of an indefinite metric, right? So you're really, this compatibility condition that we started out discussing is in fact the Laplacian of a natural neutral metric. Called neutral, meaning its signature is plus, plus, minus, minus. Now, these kind of metrics are not exactly, there's not an awful lot of mathematics done looking at these metrics. And in general, the philosophy that I've developed over the last decade is that this metric, it's nice. It's in between a Riemannian metric, which tends to be quite rigid, and a Lorentz metric, which tends to go bad. You know, you have wave equations, they break up, and you get singularity formation. But with an indefinite metric, it's kind of more balanced. In fact, it has a more topological nature. So in fact, there's some underlying topology in 4-manifold that allows you to define such metric. And the fact that it's conformally flat and scalar flat, well, they're natural geometric terms, but they're not really natural in this setting. I mean, they're not studied so much in this setting. So in particular, for example, characteristics of manifolds, as John would have called them, are hypersurfaces. They're actually null with respect to this metric. So you can kind of go back to the 30s where they didn't discuss this metric at all. They just wrote down the equation. You can see we can geometrize Fritz John and give a more modern approach to it. But the cost is you have to start thinking of metrics of signature 2-2, right? By and large, there's very little literature on such things, possibly because they haven't turned up in enough situations for people to develop abstract theories around it. Okay, so what's interesting is that conformal transformations of the space of oriented lines preserve the solutions of the ultra-hyperbolic equation. So, and in fact, you can even go a little bit further and say, well, the conformal transformations of space-oriented lines with this metric are exactly the projective transformations of the underlying R3. So in R3, you have these projective transformations which mix everything up. But if you look at what they map lines to lines, so these conformal transformations, these projective transformations of R3, they turn out to be conformal transformations of this metric. So there's a kind of trade-off between what's happening in R3 and what's happening in the space of oriented lines. So one of the questions you could ask is, so can you use the transformations to map null hypersurfaces to other null hypersurfaces, and can the inversion be improved? So this inversion that I wrote down earlier. So let me give you two alternative null. The null hypersurfaces that Fritz John used were all the lines that are parallel to the fixed plane. Right? That was the three-dimensional space of lines that was used to invert this operator. But in fact, you have alternative null hypersurfaces that you could use. You could use the set of lines passing through a fixed line. That turns out also to be a null hypersurface. And you know, if you look at a CAT scan, in a modern CAT scan, it has rays that come in from all directions on a plane. It does exactly what Fritz John does, and it scans along the person, right? And it gives you, that's where you reconstruct the image. So it is really used, this reconstruction formula using a hypersurface is really used every day in medical, medical technology. But there are alternative hypersurfaces you could use. You could use all of the, now of course there's mechanical problems. You know the shape of these, of CAT scans for big barrels, and you lie in them, and there's certain restrictions on, it's a particular setup. How exactly you would mechanically set this up, this is purely theoretical, but it is possible to invert over the set of lines passing through a fixed line, rather than all the lines parallel to a fixed plane, which is your standard inversion. Now, I'm not sure what a machine that did that would look like. It wouldn't be a long barrel, obviously. It might be something slightly different. But there would be advantages. Again, these are theoretical advantages in that less rays will pass through each individual part of the body. So you get less radiation. If you could make a CAT scan that wasn't barrel shaped, but actually used all the rays to align, if you could find some source for such a thing, you could actually have the amount of radiation that someone is exposed to by using such rays. That's one potential interest. The other you could do is you could use the set of lines tangent to a sphere. It wouldn't have to be a sphere, it could actually be any convex body. That's also a three-dimensional null hypersurface with respect to this metric. Okay, and the advantage here is that you could shield selected parts of the body as you scanned it. So if someone had a pacemaker, or they had something that you didn't want the rays to go through, but you wanted to see the tissue around it, you could use the set of lines that are tangent to some small sphere around the part or organ, or whatever it is that you're trying to include. So these are, again, alternative to this working through planes, which is the normal way that CAT scans are. Technically, you would have, I guess, when you go back to the Nobel Prize in medicine, it was given for the transform, this radon transform on parallel planes. It was two people who got it. One did the theoretical part, and then someone had to go and design a machine to do it. I'm nowhere near able to think about what kind of machine would be able to, both produce and then measure such rays, right? So there's a bit more to go before this would be in any way kind of practical, but there are certainly there are obvious advantages to using them, and maybe someday someone will actually do it. Now, as a pure mathematician, I'm more interested in more abstract things, in particular the geometrization of manifolds, low-dimensional manifolds in particular. So the background there gives you an idea of where this thing comes up, but now I'm going to talk about more mathematical applications of that equation. Because as I say, that signature 2-2 is very unusual, and it's hard to really, to place it. It's not relativity, but it's not positive definite, so it has all kinds of problems with it in some ways, even aside from a lack of familiarity. So let me talk about geometrization. As we all know, again, very briefly, you have an n-dimensional smooth manifold. It's topological space, locally diffeomorphic to Rn, and you want to try and categorize it in some kind of way. So when you go to 2 dimensions, so for closed surfaces, I guess the classification of all closed surfaces was you can put it down to Dane and Heegard back in 1907. So again, the closed genus G surface, and it's a Riemannian metric, so you impose geometry on it, and you find that only one type of nice geometry fits each individual topology, or at least in big groups, at least the genus greater than 1 you have to have altogether for a negative curvature. So then you go on to what happens in 3 manifolds. Well, again, this is much more recent, obviously, and more or less with Pearl in 2002. So again, here you have closed 3 manifolds. It can be split into pieces, each of which admits exactly one of these 8 Riemannian homogeneous metrics. Now, it is true that of these 8 different manifolds, there's 3 that are kind of, R3H3S, and after that, they tend to have also canonical indefinite metrics on them. So if you look at some of the groups, Heisenberg group and that, you can define naturally invariant indefinite metrics on these spaces, but generally we stick with the positive definite ones and, of course, the classification of 3-manifold, one of the high points of the mathematics in the early 21st century. The problem with closed 4-manifolds. So this is really the question I want to try and put across, how the ultra-hyperbolic equation certainly can help in some way. So the problem with closed 4-manifolds is that there are no natural family of Riemannian metrics. In the case of 3-manifolds, it's homogeneous in 3 metrics. In dimension 2, it's it's constant curvature metric, yes, curvature. So what about dimension 4? Well, 4-manifolds don't have any very natural. There's no real Riemannian metrics that have emerged that captures all the variety of 4-manifold topology. And 4-manifolds also have difficulties that are not encountered in other dimensions. As the dimension gets bigger, your problems grow. And 4 is already a lot worse than 3. In particular, the fundamental groups of closed 3-manifolds, you can write them down what they could possibly be. Quotients of certain well-known groups by actions that have some nice properties. That can't be the case for 4-manifolds. So in particular, it's known that any finitely presented group can be the fundamental group of a smooth, closed 4-manifold. Now that completely scuppers you because, of course, finitely presented group, you know that there's no way to classify them. It's known that this is already a completely intractable problem just from the point of group theory. So you don't have any good models for what their fundamental groups could be. Now you could, of course, and what people have done is, of course, let's just look at simply connected 4-manifolds. That puts that whole question aside. Let's just deal with simply connected 4-manifolds, and then we don't have to worry about finite presented groups. Other problems that arise, well, in any dimension, this is a problem, so it's not specific, but higher dimensions manifolds, you have surface, in 3 dimensions, curves can be knotted. In 4 dimensions, surfaces can be knotted. So the problems escalate in terms of trying to cut them up, like in 3-manifolds, you cut them up and you put them into pieces, prime pieces, and then you cover them by lines. So there's a whole theory behind that. For 4-manifolds, you're going to have a lot more problems. Sure, curves can't be knotted because you can only, but now you have surfaces being knotted in 4-manifolds. So that is a serious escalation in the difficulty of the problem. And the other thing is, and this is one of the key things that makes dimension 4 different to higher dimensions, is that if you have a generic 2-dimensional disk in 4 dimensions, generically it's only immersed, it's not embedded. So if you look at the theory of higher dimension 5 and above, Poincare conjecture and 5 and above, all of these big topological theorems, one of the main things you do is you use these disks to pull curves over, etc. And you always have a disk in higher dimension that's embedded. In 4 dimension, a generic disk will have self-intersections. And so therefore, a lot of the techniques, all of the techniques developed by Snail and by Mort Brown for higher manifolds means that you can't prove the 4-dimensional smooth Poincare conjecture in dimension 4. Whereas in dimension 5 and higher, it's all been proved. So you have this anomalous situation where lower dimensions are tight enough that you can prove things. Higher dimensions, you have so much space you can prove them. But suddenly in dimension 4, you have this in-between thing where none of your standard techniques seem to work. So let me, again, a few comments. So we can avoid problem 1 by restricting to simply connected 4-manifolds. Let's just sweep that whole problem with the finitely presented groups under the table. And then problem 2, well, we're not going to get away with it, or we're not going to deal with that. But problem 3 means, as I said, that most high-dimensional techniques don't work. In particular, there's a thing called the Whitney trick, in which you take an embedded disk and you do various things in 4-manifolds, a kind of key thing in topological 4-manifolds and smooth 4-manifolds, and you can't do it in dimension 4. It's just the dimension where 2 plus 2 equals 4, and so you have self-intersections. Okay, so the idea is that you can actually use neutral metrics in this set. So unlike Riemannian metrics, a neutral metric, so a neutral metric is just one of signature 2, 2. The example I gave you was the space-oriented lines. So a neutral metric is sensitive to the underlying topology of the manifold. In other words, you always have Riemannian metrics on any 4-manifold. You do not all closed 4-manifold. You do not have neutral metrics on certain closed 4-manifolds. I'll give you the conditions now in a minute. So somehow the metric, whereas if you look at in 3 dimensions, somehow you're classifying 3-dimensional spaces by the curvatures associated with the 3-dimensional Riemannian metric on the manifold. That's the, the Thurston approach. Here, you don't have that, but you can introduce these neutral metrics, and you forget about the curvature. Even having a neutral metric on a 4-manifold, already closed 4-manifold, already puts topological restrictions on it. So there'll be certain classes that will have these neutral metrics and certain ones that won't. So the idea again is to use a neutral metric on your 4-manifold that somehow fits the underlying topology. That's the basic idea for using these metrics in this setting. So in particular, for codimension 2 constructions, you can geometrize them using neutral metrics. So the idea is to have a kind of an alternative form of geometrization, just like the geometrization of 3-manifolds, which will be useful in certain categories. As I said, you'll never get away from that problem with non-simply connected ones. But with simply connected 4-manifolds, there may well be a possibility that you could use these metrics on certain types. So there'll be the positive definite case, and then you have the, you might even have the Lorentz case, but you would also have these codimension 2 metrics, these metrics with signature 2, 2. So the first thing that you start, when you look at that, you realize, okay, not every closed 4-manifold even admits a metric with a neutral signature. There's a topological obstruction to the existence of these neutral metrics. In fact, it's equivalent to admitting a pair of transverse planes at each point of the 4-manifold, the whole way around. So a classic result of Herzbruch and Hopp from 1954, they were looking at plane fields on manifolds. In fact, how they were doing it is to show if you have a smooth closed 4-manifold and it admits a neutral metric, then the Euler characteristic plus and minus the signature, the Herzbruch signature of the manifold, the topological invariance of the manifold, that they must add up to 0 mod 4. So you can quite clearly, you can write down exactly which 4-manifolds, closed 4-manifolds, admit neutral metrics. And in fact, if your underlying, this is true even if your n is not simply connected, but if your 4-manifold is simply connected, these conditions are both necessary and sufficient. So for simply connected 4-manifolds, this is the condition for you to even have a neutral metric. For about curvature or nice properties, just even be able to define it without singularities. So, for example, neither S4 nor CP2 admit a neutral metric. So there's topological obstructions because they do not satisfy these conditions up above. Whereas S2 cross S2 and the K3 manifold, another well-known closed 4-manifold, do it. So you can see that neutral metrics, when you talk about closed 4-manifolds, neutral metrics are going to be like a whole category of manifolds that you can, use these metrics to try and explore. But if you have other manifolds, even some of these simple manifolds, unfortunately, your metric might have singularities. Okay, so just to fill out the picture, let me just mention one other structure that we're going to use in what follows. So it's what's called a para-complex structure. So we're all familiar with complex structures, which is, an endomorphism of the tangent space whose square is minus the identity. A para-complex structure, or almost para-complex, it's an endomorphism which squares to the plus the identity, but is not equal to the identity. So it squares to the plus the identity, and not only that, but in fact, basically it's like 1, 1, minus 1, minus 1, but it's as an endomorphism of the tangent space. Now, we would like such a para-complex structure to fit with an underlying metric. Now, if you allow indefinite metrics, there's kind of 2 ways that you could do that. It could be isometric with respect to metrics, so that if you put your j in on both of this, the inputs into metric, you just get the same thing, or it could be anti-isometric. And we'll say it's parallel if it's covariant to 0 with respect to the underlying metric. So these almost para-complex structures, sometimes they look a bit like complex structures in some sense, but they're actually really more like a product structure. So you can imagine you're splitting your 4-dimensional tangent space into 2 blocks, and you put the identity here and minus the identity down here. Right? And then when you square them, you end up with the identity, and well, you can find these properties. Again, it depends on the metric. By the way, the metric here would have to be indefinite. So I'm allowing this G to be positive definite or indefinite depending on the circumstances. Okay, so this extra structure, this paracomplex structure, is defined very naturally. So if you take an oriented line and you take another oriented line and you reflect one line in the other, so you just drop a perpendicular, so you have this fixed line, and you take this line here and you go perpendicular and just same distance each side, you get a mapping which takes this reflection in the line, and reflection in the line gives you already gives you an almost paracomplex structure on the space of oriented lines. So here's an example. It's anti-isometric in that it flips the sign of metric. It's plus, plus, minus, minus, and then when you do J, it's minus, minus, plus, plus. But it's not parallel. This is not a Kähler structure. So the covariant derivative of the J is not zero. So it's not Kähler. It's not parallel. But here's an actually defined paracomplex structure on the space of lines. Now, I guess in some ways, if you think of your paracomplex structure, if you take your four-dimensional tangent space, you just split it into two planes, you can say, oh, make it +1 the identity on one and minus the identity on the other. There you go. That's an almost paracomplex structure. Right? So you can certainly define these things over 4 dimensions, but as you move around the manifold, it may not be parallel. In general, they won't be parallel. Okay, so in particular, if you take an isometric almost paracomplex structure, it's parallel if and only if these two plane distributions, these eigenplane distributions, are tangent to a pair of mutually orthogonal foliations by totally geodesic surfaces. So you're slicing, it's like your manifold looks really like a product. Locally, it's exactly a product, and the Riemannian metric, the indefinite metric one is also, it's got this kind of splitting into the two. So you get and each of them is integrable, each of the splittings is integrable, and they're totally geodesic. So being parallel is a very strong condition, and essentially says your 4-manifold looks like it's just splitting into a product, maybe an S2 cross S2, or two surfaces. Similarly, if your J is a parallel isometric paracomplex structure on a Riemannian manifold, and if you take your Riemannian manifold metric, here's your Riemannian metric G, and you just put J in one of the things, what it does is it flips, gives you a new metric, and this metric is indefinite. So if you have one of these paracomplex structures, or almost paracomplex structures, and you stick it into a metric, it kind of flips the sign on two of the eigenvalues. And so, whereas this metric here is positive definite, after you put the J in, you get a new metric, and that's going to be neutral. It's going to be signature plus, plus, minus, minus, like split. Okay, so what's interesting in that is, well, if your complex or your paracomplex structure is parallel and isometric with respect to the metric, well, then if you do this, your positive definite metric is Einstein if and only this guy, the indefinite metric, is conformally flat scalar flat. So in the space of oriented lines, we saw that the metric was exactly conformally flat scalar flat. I mentioned that back earlier. So what this is saying is there's a kind of a duality between, if you have one of these parallel complex structures, parallel paracomplex structures, you have Einstein metrics, and you hit it with J, and then you're going to get one of these conformally flat scalar flat metrics. Okay, so in some ways, the metrics that you're getting on the space of line, they're kind of like the neutral equivalent of Einstein metrics, very similar to Einstein metrics. Now, the only difference really is they're not integral in the case of geodesic spaces. So, in fact, you can't just do J and get an Einstein metric on the space of oriented lines, for example. It's not integral. So here, I did assume that it's parallel, but in that case, you get this duality between positive definite Einstein metrics and split signature or 2-2 conformally flat scalar flat metrics. So there's a kind of payoff between that. Now again, isometric being parallel and isometric are quite strong. In space oriented lines, that's not true. That's why you don't have a natural Einstein metric on the space oriented lines. It's because the paracomplex structure is not parallel. It's not isometric either. it's actually anti-isometric, as I mentioned. So this is a little bit out, we're kind of pushing the paradigm out a little bit from what you have in geodesic spaces. There are good models for certain types of neutral metrics and this kind of behavior, but at the same time, unless they're parallel, you don't have this exact back and forth between Einstein and conformal flat scalar form. Okay, so next we can say, well, okay, what closed metrics have these parallel isometric paracomplex structures? And again, it's a topological condition. This here was the Hertzsprung signature that appeared in the formula earlier. So you have topological obstructions arising for nice metrics. Now, of course, you have a parallel isometric paracomplex structure and an Einstein metric. You put them together and you get a conformal flat scalar flat neutral metric. So this is saying you can't do that unless this 4-manifold, its signature, the Hertzsprung signature, this topological invariant, is 0. Similarly, well, as a corollary, I suppose you can say the K3 4-manifold. So this is this, it plays a big role in 4-manifold topology. It's a closed 4-manifold, as well as complicated second homology, but it admits a Riemannian-Einstein metric and isometric, almost paracomplex structures, but they can't be parallel. So you can't. It doesn't. If it was parallel, you can't expect it just to fall apart as a product. So what you find is that these paracomplex structures, they're like an almost product structure. As I mentioned earlier, in higher dimensions, they're actually called almost product structures. It's like your manifold is being split in two as you go along at each point. And if it's integral over the whole manifold, eventually, and you have enough geometric conditions, then in fact it will be a product. So you find certain manifolds that admit these metrics. Now, notice that these metrics are, they're indefinite metrics. Their signature is restricted, or sorry, their existence or otherwise is restricted by Hertzsprung-Kopf. But here now we find curvature restrictions also on which manifolds, like these neutral metrics, are nice neutral metrics and which ones don't. Okay, so I'm mentioning there about complex 4-manifolds with these neutral metrics, either compact. Generally, I wouldn't assume metric as any singularities, but if you allow it to have a few singular points, they actually have a well-defined index. So, in particular, so if you have a neutral metric, singular points on a closed 4-manifold, isolated singular points, then there is a bi-index which you can define. It's like a Hopf winding number, but it's in higher dimensions. And so it's two numbers. It's an element of Z cross Z. And they're associated with each singular point on this closed 4-manifold. What's also interesting is that the sum of these indices is a topological invariant of the neutral manifold. So it's related to the characteristic classes, and it's also related to the signature and to the Hertzsprung signature and the Euler characteristic of the manifold, but they're topological invariants. So just like you can take a tree manifold and look at a vector field, and if count the singularities, count the indices of the singularities, you can add them up and you'll get the Euler characteristic of the tree manifold. This is the same thing in some sense, but now it's more complicated because you're in 4 dimensions and your index is actually 2 elements of Z, and you can add them up and they give you topological invariants of the neutral 4-manifold. In fact, you can go further. These actually can be expressed in terms of integrals of the curvatures of the metric. So you can actually write down an explicit formula for these topological invariants as integrals of curvatures of the underlying neutral metric. The other thing that's kind of interesting.
This is a kind of Gauss-Bonnet theorem.
Exactly. So it involves, it's like Gauss 1A plus signature. So what you have in 4 dimensions that you don't have in 3 dimensions, where you have your Euler characteristic, of course 0, but now you have Euler characteristic, but you also have the Hertzsprung signature, this tau. Yeah? And so these 2 invariants. Yeah. So here, these are adding up to things that in fact involve exactly the Gauss 1A, the Gauss invariant, and also, as I said, the signature, Hertzsprung signature. Okay, but again, this is on closed 4-manifolds. So if you like, as I said at the start, you have obstructions to existence this is by Hertzberg-Hoff, there are existence to neutral metrics on 4-manifold, closed 4-manifolds, which if you give them singularities, then they all have these nice indices. And these indices almost add up to, you know, some particular expression which you can write down in terms of integrals of the curvature. So that's for closed 4-manifolds. But probably what's a bit more moving on is not to look at new 4-manifolds, but look at neutral 4-manifolds with boundary. Now, what kind of boundary is natural for a neutral 4-manifold? Well, a null boundary is the most natural. You can construct interesting things in geodesic spaces with null boundaries. Well, what's interesting is when you have a neutral 4-manifold, you get a little bit more, you get a lot of information. Neutral metrics have a lot of kind of topological information in them. In particular, the null boundary. So if you have a null boundary, well then, in an indefinite space, the normal to a null hypersurface lies in the hypersurface. So it foliates the hypersurface. Its own normal foliates the 4-manifold. Right? This is true quite generally. However, here the null boundary has a canonical foliation, and it has even a little bit more. So it tends to have a lot of this. The metric somehow degenerates at the boundaries. Some job here. Okay,
This should be there.
so you're not. It has a pair of foliation factors. So it has this foliation, but at each point it has the metric is degenerate. So if the metric is degenerate, it has two what are called totally null planes, planes on which the metric is exactly 0. So you have the tangent here, and you have a kind of a blade structure. It's like a double blade structure. And then you have winding numbers of these as you go around this null geodesic. This will be a null geodesic. And these can give you expressions precisely for these topological invariants. Now, what I would say is, okay, so all of this I'm saying is unpublished, but at the same time, you can trace it back to Hertzberg-Hoff, but you're doing the boundary case, and you're imposing a null boundary, right? So Hertzberg-Hoff and Fritz John, they only considered open manifolds, or they considered compact manifolds in the case of Hertzberg-Hoff. But if you allow the boundary to have a neutral metric where the boundary is null, well, then you find that there's a lot of interesting information that you can find about the 4-manifold just from the boundary. So, in fact, I'll claim a little bit more. So, if you know this foliation at the boundary, not only is it a foliation and it has these two plane fields, and so you're going to have they're all twisting around each other. That information alone, I claim, can be used to reconstruct the interior of the manifold. So you're only getting information at the boundary, the 3-manifold boundary. It's a lot of information, right? It's a foliation and a pair of planes at each point, and they twist around each other, etc., etc. But what they're telling you is really how the null surfaces in the interior are behaving, right? So, in fact, this, if you like, we're X-raying the inside of the manifold by knowing what it looks like on its null boundary, knowing what this foliation looks like. You can reconstruct to a certain extent. Now, the full, I'm not exactly sure of the full parallel method, but certainly in lots of circumstances, you can see from the boundary exactly what the topology of the interior has to be, modulo certain things. So again, the idea is to use these neutral metrics in a topological way, is to use them to try and see what the inside of this 4-manifold is just from the null boundary. That would be one application or one way to use this neutral metric. On the other hand, if you have it on an open 4-manifold, so without boundary, well, that's also an interesting case. In fact, that's the case of spaces of geodesics in general. If you do a conformal compactification, then you end up with some nice conformal data at the boundary. In fact, there are conformal invariants that you can define on the ends of these open neutral 4-manifolds. They come from this foliation, this compactification, and because you're doing it conformally, the null structure doesn't change. So you can capture this null structure in this 4-manifold by conformally embedding it in a 4-dimensional space and looking at the ends, one with boundary. So again, good examples of this is space-oriented geodesics. So the space-oriented geodesics of OR3 is mentioned as TS2. So it can be embedded in S2 cross S2, it can be conformally embedded in S2, and you end up with a sphere at infinity. And at the sphere at infinity, you can see some of the geometry of the interior of the manifold. So it's quite, it's a kind of a holographic principle. I guess this is like an early version of what's considered now and more, with a lot more structure. They're called holographic principles, where the boundary of the 4-manifold can tell you a lot about the geometry of the inside. And again, the kind of new element here, if you like, is the fact that these metric being 2,2 carry. They're not as rigid as as positive definite, and they're not as bad as Lorentz, where things can go really bad. 2,2, this balancing of the metric somehow allows it to carry more geometric topological information than, in fact, either of the other two signatures, in fact, do in for 4-manifolds. Okay, so that's a brief overview of many different aspects of that. So I'll finish there if there's any questions.
Thank you. Let me stop the recording. Oop.